engineering subject, specifically in the area of sneak circuit analysis role in concurrent engineering. Tyrone Jackson and Jeffrey Miller. Our first speaker will be Tyrone Jackson. Tyrone is presently a senior staff engineer in product detectives at Hughes Radar Systems Group in El Segundo. He will be addressing the applications of sneak circuit analysis in concurrent engineering and why the primary objective of computerized tools should be used to support team relationships rather than processing data. And then Mr. Jeffrey Miller is presently a senior system engineer at Sohar, which developed the circuit analysis tool called SCAT. We'll explore identification of sneak paths in switching circuits without having to generate and analyzing a network tree representation of the circuit in part by applying analysis to individual assemblies and their interfaces rather than the whole system. His talk will cover the applications of using the SCAT tool. So I'd like to introduce our first speaker, Tyrone Jackson. Tyrone.
Thank you, John. To begin with, what I'm going to discuss is a more global viewpoint of sneak circuit analysis, rather than just talk about it as a problem-solving tool. I'm going to talk about how sneak circuit analysis actually fits into the overall concept of total quality management. The topics of discussion are going to be, to begin with, I'm going to talk about exactly what elements of total quality management are and show where sneak circuit analysis and other analyses and other concepts fit within the TQMS framework. I'm going to explain what sneak circuit analysis is, and that's essentially a fault failure analysis technique. And then I'm going to talk about steps followed in performing sneak circuit analysis on the TQMS, which consists of these steps. Accessing the need of sneak circuit analysis to meet the customer requirements, definition of the current design process, determine what should be the optimal sneak circuit analysis methodology, and then afterward, after you've done these other steps, organize a team of qualified practitioners to actually perform the analysis, and then the conclusions drawn from these topics. Okay, here is a material relationship showing how TQMS is supported by the various elements that should be considered in an organization. To begin with, you should consider creativity, performance, leadership, membership, mass management, quality, and all the things that quality is made of. Now, sneak circuit analysis fits down here under engineering analyses, which is one of the product tools that increase the skill and improves the processes. Simply looking at sneak circuit analysis as only a tool and not considering how the main purpose of this tool is to improve the quality, and how improving the quality is really a part of a company becoming more competitive, you will not adequately apply the tool. You have to consider the entire scope. And that scope also consists of things such as attitudes and relationships. Relationships and communication are very important. For those of you who may not be familiar with what sneak circuit analysis is, it's basically a topological technique. It's a modeling technique that's used to identify unintended paths, circuit paths, and it's also used to identify things such as unintended timing, indications, and labels. This technique was developed by Boeing in 1967 under categories of SNCs. The SNC paths are the ones that people are most familiar with. But there's also SNC timing, SNC indications, and SNC labels. The characteristics of a SNC path can be basically described as a reverse current path on a circuit. Current which is traveling in a direction that's unintended, and it creates functions that are unintended. SNC timing characteristic is essentially an event that happens out of sequence. It's an unintended event. SNC indications are simply false displays or test equipment, or displays on monitoring devices. SNC labels could be labels placed on operator controls that cause operators to take actions which are unintended. All of these are events that can cause a system to fail, but not necessarily due to a hardware failure. Here's a general explanation of the application criteria for SNC circuit analysis. You should consider applying analysis if it's a highly critical system in which the failures can be catastrophic. Systems which have exhibited some unknown events in the past in which the causes were unexplained. Now here is a matrix that puts SNC circuit analysis, the type of problems that can be addressed by SNC circuit analysis, and perspective with other type of analyses that you may be familiar with. For instance, take a look at the type of problems addressed by SNC circuit analysis, such as operator errors, latent time and SNC paths with hardware FMEA. You can see that no one of these analyses covers all the types of problems that you would encounter in design. So there is no one panacea approach to solving problems. You can't apply FMEA by itself, fault tree analysis by itself, or any of these by themselves. You should try to combine, first figure out what type of hardware is applicable to the type of problems that occur, and then select the type of analysis technique that's necessary. Okay, now let's take a look at, well, what do you do? How should you perform SNC circuit analysis under a total quality management system? Well, the first thing you should do is you should assess the need to begin with of even the need to even perform the analysis. Next, you should define, if that need is there, only if that need is there, then you should define the current design process to make sure that you fully understand all aspects of the process and that how SNC circuit analysis will fit in that process. Next, you should, after defining the process, you should then select the type of SNC circuit analysis method that best meets the needs of your design process and the needs of the design requirements. And then only after you've done that, then you should select the type of people who can perform this type of methodology. Okay, to assess the needs of SNC circuit analysis, you first have to translate the customer requirements into design and process characteristics. Next, you have to determine how each characteristic actually needs to be controlled. And then you have to identify relationships between the characteristics and the types of problems assessed by analysis itself. follow to define the process. To begin with, you have to flow diagram the process. In flow diagram the process, you would identify all the inputs and outputs. This is pretty much what you do if you do a traditional FMEA or event sequence analysis. You start with a flow diagram where you identify all inputs and outputs. Then you determine the techniques and tools applied in each task. You identify the major players and what their responsibilities are. Then you identify the methods of communication. Communication is very important because the method that you're actually going to apply to do the sneak circuit analysis may have to use some of these tools that are already in place to expedite having the problems that are identified actually remedied in the design. And then last you examine the task schedule. Okay, now the objective during your design is to perform your task concurrently. What you don't want to do is have your design be done in serial manner where first the performance is designed and then it goes to reliable engineer, then it goes to durability and testability and safety. Because then what you'll be doing is going through design changes rather than avoiding them. Okay, that was the first step that you took to determine if the sneak circuit analysis was required. The next step is to actually identify which methodology you should apply. Now, there are several types of sneak circuit analysis methods that are being used. The initial one, developed by Boeing, consisted of a tool that found sneak paths, and then it used topological diagrams to identify the other type of sneak problems, such as the sneak timing, the sneak labels, and sneak indications. That was a very labor-intensive technique. Now, during the last 5 years, there's been other tools developed, and also other techniques. There has been a technique which combines sneak circuit analysis with failure modes and effects analysis. There are tools available that can identify design concerns, and some of these tools have been ported to the PC. So you have to look at your design and then assess, well, which type of tool would best suit you. And in a lot of these cases, some of these tools are only being used by vendors, and you can't use the tool yourself. So you have to also factor into the additional cost of a vendor, of the vendor cost of doing analysis for you. So one of the things you should do is, in your decision, is come up with a quantity versus cost diagram. Figure how much it's going to cost you to do the analysis. And by the way, this is usually the traditional approach used to figure out what the ultimate cost of the analysis is. Figure out what's the cost for you to do the analysis based upon quantity. And if what you're going to do is less than what the vendor is going to cost, then you do it. If it's more, then it actually should be done by a vendor. Here's an overview of the most fundamental sneak analysis method. Now, regardless of what other automation is in some of these steps, this is usually the way it's done. It starts out with some type of data preparation. Now, whether that means a net list is actually being read by a CAD system, or someone sitting down and typing the information in. It's input in some manner. Some design is actually inputted to the computer, and it generates usually a net list. Okay, now that net list, okay, and there's two steps to that. One step is there's your box data, which defines your cards, and the next step is your interconnects or your wireless. See, you can have several cards, but if you don't have correct definitions or correct net lists for your interconnects, then your analysis won't be effective because you won't be able to trace the paths through your circuitry. So actually, there's two sets of data that has to be input. Okay, now that's processed by a computer program. Now, during the course of that process, all the paths in the circuitry are traced, and what's created is network trees. Now, network trees partition the paths into powers and all the paths that the current flows through to the ground. Now, the network trees are either manually created or they're created automatically by a computer. Now, initially in the first sneak circuit analysis tool developed by Boeing, you had to draw the network trees. But once you drew them, you could automatically see the reverse current path. It was labor intensive, but the technique became quite effective because once you drew those network trees, it would identify your sneak paths. Now, your other sneak conditions, your timing, your indications, and your labels, those were identified manually, but sneak circuit analysis gained its reputation for being labor intensive, but it was effective. It could identify problems. And the way they did identify the problems were clues. Now clues are basically by experience. You would give an analyst a list of clues, and then he would, and these were actually problems that were discovered before. He would have this list in front of him, and this would sort of enlighten him to the possibilities of failures, and it would it would actually help him identify sneak conditions in systems. And then finally, he would generate sneak reports. Here's a full diagram of that process. And as I said before, regardless of what tools are being used, the process still pretty much flows this way. Now, certain steps might be automated by some tools, certain steps might be manual, but the process is still basically flows this far in this manner. Now, one of the fundamental questions that you should ask yourself when you're doing sneak circuit analysis is, why am I doing it? Okay, to begin with, not just to ponder through that you have a schematic there and you're going to go through the steps of building network trees and then finding sneak paths. But the real reason is, why am I doing it? Okay, the reason that it should be done is you're trying to design in sneak circuit durability. You want to design in the durability against sneaks, not find sneaks. Okay? So in order to do this, you have to be in there early enough in the design to do that. One of the major problems in the past was that because it was a proprietary technique, Boeing would only analyze the circuits after you given them finalized designs, and if you found anything, you would have to go back and redesign the system. You don't want to be locked into that mode. What you want to do is actually have the analysis done in a process of developing your design, so that when your design is completed, you won't be out there having the equipment in the field before your sneaks are gone. Here's a representation of what I just said. You want your durability features, which would include your sneak circuit analysis durability features or whatever, input into the design, not added on when the equipment's in the field. How do you do that? Design rules. there's many snake clues that can be, and there are, converted into design rules. Too many snake clues are actually being used only to identify snakes rather than to translate those clues into design rules so that the snakes will not be designed in the first place. Now, only recently, SOHAR issued a document under funding by RABC in which they listed design rules which can avoid the inclusion of snakes. But there needs to be more. Okay, this chicken and egg picture is being shown here to make a point. The point is that the TQM, there are common objectives for all the tasks in TQM, and those common objectives should be focused on the quality of the equipment. You should be doing all of these tasks primarily to enhance the quality of the equipment. Too often, the task-specific objectives become more important than the end objective. And where reliability engineers hear this more often is what's become of the FMEA. Too often the FMEA report is really the end objective. And what did that FMEA do for the design is not. So to avoid snake circuit analysis or any other analysis that's done during the design process, you should keep your end objectives at the primary focus. In order to make TQMS work, all your tasks have to work together. They can't work if one task isn't working in conjunction with another, or if there's protectionism, or if there's isolation because of programs. If you have a reliability program, a thermal program, and a durability program separate, and everybody has their own separate goals, that's all right for the past, but for companies to become more competitive, you have to be more concerned about the individual objectives of the task working together for the end objective of the quality of the product, rather than being worried about the reports. And this is pretty much what happens when you worry about the reports. To show this in another way, the road to continuous improvement is taken by the TQMS point of view of the tasks should work together, and you should not organize your tasks into programs. By organizing your tasks into programs, you lose sight of the end objectives of the quality of the product. Okay, so once you have defined a process, and once you have decided exactly what technique you're going to use based upon whether or not you can get automated tools, or based upon whether or not you're going to vend a tool, or based upon expertise of your own people, you take all that information and then you start organizing a team. But the team has to be organized based upon whatever is available for communication. You should focus on the problems that can be identified, not the fact that certain people have certain positions. You have to brainstorm once these design rules are going to be implemented. You have to work as a should not be concerned about, well, I'm gonna do my job, and then I'm gonna give you a report, and then what you do with that report is up to you. That should not be the position you take. The position should be, I'm doing a task to support design and quality. So your relationships become more important than the tools you use, because you're working as a team. And last but not least, you have to clearly define responsibilities. Everybody should have take ownership for their work at their level, and they should be given a control at their level. Okay, now, who's going to help all this to happen? There needs to be a facilitator. I use the word leadership here. There has to be a certain amount of control. There has to be planning, and the risks have to be assessed before you begin. There's always risks in everything you do. There's risks in success, and there's risks in even achieving costs and schedules. You have to understand all these things before you start, and this has to be assessed by a third party, someone who's actually over the team. Here's a graphical representation of the things that should be considered in leadership. Anytime you propose anything different, there's going to be a cultural change. You're going to have to address that. You can't ignore it within any organization. You have to understand what the requirements are to perform the task, to achieve it. You have to have control of the schedule, and you have to delegate the responsibilities and have everyone buy into it. And then you have to generate documentation to solidify basically what the team agreement is. See, this type of organization will work, but simply taking this point of view of having responsibility to apply a technique and not considering all of these others will not necessarily improve the quality of your product again. If SNC circuit analysis is a tool and you have to increase the skill of your people, then they're going to need training. You're never, ever going to improve the skill of your people without training, no matter how good your tools are. So you have to remember that when you acquire a tool, and you have to clearly understand what the training requirements are to effectively use that tool if you're going to increase the skill of your people. So in conclusion, no matter what technique is being examined, SNC circuit analysis is not presently fully automated. I mean, no one has a tool that can completely automate SNC analysis. Therefore, since you don't have a tool that can do it automatically, team interaction is your most important factor to successfully have it done. You have to consider those aspects of who is going to identify the SNC paths, who is going to identify the SNC timing. Those may not be the same people. Your reliability people may have to construct the network trees, but your design people or your thermal engineering people may have to take on responsibility of identifying some of these problems in the models. But just simply giving a responsibility to a particular area will not solve your problems. So you have to keep in mind that the relationships of the team and really understand what the issues are very important. should support the team framework. They should not be such that they encourage separatism among disciplines. The sneak circuit analysis tool, well, the method that's actually being applied should be tailored for the type of product. All methods aren't applicable to the same type of product. For instance, the GM cars are more interested in what happens on grounding studs and what happens when fuse is short than would be in electronics. You know, we wouldn't be concerned about that. So what they would want is they want an inclusion of hardware failures in analysis. Now, for digital circuitry, that wouldn't be a case. So there is no blanket approach. You have to look at the product first and then determine what technique is going to be applied. There is no blanket tool either. And last but not least, the training, sure, you need training in the methods and the training in the tools, but also you need training in understanding exactly what TQMS is. TQMS is more than just training and tools. This is more than just tools and techniques. It's training, it's relationships, it's attitude, it's everything that I've shown on that other matrix showing you what leads up to TQM. And that concludes my presentation. Are there any questions?
Thank you, Tyrone.
There should be at least one question.
One question. Herb Gaucher's got a question.
Okay. Your approach is the teamwork approach and tying it all together with TQM.
Right.
Okay, that may be an approach. But isn't it the responsibility basically of the designer who does the basic analysis of that design and who has to know what the functionality is, okay? Particularly the systems engineer are involved with affecting all the functionality analyses.
I agree.
Shouldn't that be the basic responsibility, just tying in sneak circuit as one additional factor to consider when they're going through that functionality analysis?
Okay. Actually, except for taking the schematics to the factory floor and working the turret lathes and the drill presses, the designer he's responsible for everything until it reaches that factory floor. Okay, you agree with that? But
well, today they don't do that.
Okay, but see, the problem is the design cycles are getting shorter. Okay, as the design cycles get shorter,
Exactly.
as they get shorter, what the designer has time for gets less and less. Okay, now it would be nice if we had tools that could allow the designer to do all the things that he would like to do in less time. That would be the ideal situation.
Yeah, but he is doing that.
Okay.
He now operates using Mentor or different kinds of software to
That's right.
He looks at his whole, he has access to his entire design circuitry.
That's right.
Through the computer.
That's right.
And so on.
That's right.
And now, shouldn't we be adding this one additional capability of analysis to the methodology he's already using for assessing the functionality?
Well, we should if we could, but we can't.
I don't know about that.
Well, I'm telling you we can't.
Well, I don't know if I should believe you.
Whether you believe me or
What
not,
I'm saying
there is no tool.
Yeah, what I'm saying to you, well, the gentleman's going to tell us about the tool, but what I'm saying to you is that your approach is the team approach.
And I'm saying it's forced on you. I'm saying it's forced on you.
That's designed by committee. And you know, when it's designed by committee, you get an elephant.
That's
Or is it a
ill-advised question he's going to ask you.
I was going to ask you about committees.
Now, don't think about my question now.
Thank you, Irv. Thank you, Tyrone. My name is Jeff Miller. My company is SoHard. We're involved in analysis, development, design activities that are related to reliability of critical computer applications. And one of those endeavors was sneak circuit analysis. Approximately 2-3 years ago, we were working on a contract for the Air Force to develop a sneak circuit analysis tool that could be integrated more with the design process. And I'm here now to tell you the results of that endeavor, along with various enhancements that we've done after that contract was successfully completed. I first will just briefly touch on the background of sneak circuit analysis. Tyrone already mentioned the fundamentals, so I'll just touch on a few of the specifics that are related to SCAT. Then I'll talk briefly about a manual procedure that we developed that was the precursor for our automated procedure. And I'll show you some highlights of it and an example of that, of the use of that procedure. Then some conclusions and some sources for further information. First, a very simplified example of a sneak circuit. In this basic circuit, the goal is to open the cargo door, but only enable it under normal conditions when the landing gear is down. To accomplish this, the normal door open switch can only be activated when the gear down switch, when the switch indicating that the landing gears when the weight on wheels switch is activated. Under certain emergency conditions, you might want to open the cargo door while you're still in the air. In this case, there's an emergency switch. That was the intent of the circuit. What was overlooked was the possibility of engaging the emergency switch while the normal switch had been also engaged. Under those circumstances, you have a sneak path. You could send power back through the normal door open switch and to the landing gear, and inadvertently lower the landing gear. The point to be made is this path here. Under normal conditions, the power progressed from left to right through the switch. That was the intent. Under abnormal conditions, power was going from right to left through that switch. A so-called reverse current path, or another way of saying that is this segment is a bidirectional path. The solution, put a diode in here to block that reverse path. Sneak circuit analysis is documented in Mill Standard 75, in Mill Standard 1543B. It's a formal task. It's been defined in the standard, and it's a procedure that's by Boeing, and as Tyrone mentioned, these are the major activities associated with sneak circuit analysis. Our endeavors concentrated primarily on automating the search for sneak paths and the search for design concerns. In these two areas, particularly with regard to sneak paths, the conventional approach is very labor intensive. You do need the specialized knowledge of certain vendors, which means perhaps turning over your proprietary designs to these people to perform the analysis. And the results are usually only available to you late in your program, typically after at a point in the program where it's very expensive to make changes. What we hoped to do was to provide a method of introducing the analysis earlier in the development phase, so that the engineer can get his results in a timely manner and incorporate it into his design when the cost of doing so is still low. In the conventional approach, we would take our simplified circuit, as I showed here, and we would translate it into a network tree, as I show here. In this case, using the formalism of the procedure, we can more easily see a pattern. It's the so-called H pattern, where the crossbar of the H represents the path that can conduct current in either direction. And this serves as a clue to the analyst. He would look at this crossbar and say, right away, here is a potential for a sneak circuit. He would then have to ask himself, well, was that the intent of the circuit? If not, could anything detrimental happen because of that reverse current? The answer is yes, then you have a sneak problem. What our program attempts to do is to automate this process without having to draw this network tree and without having the analyst search for these patterns. Before doing so, we developed a manual procedure. The manual procedure had two major goals. One was to provide design rules that the design engineer could review prior to his design and during the early phases of his design to guide him away from certain circuit configurations that are historically known to be prone to sneaks. The second part of the manual procedure is to help the designer review his circuitry to spot certain conditions that are associated with sneaks. In that regard, we provided design rules. These are basic rules for the designer to review. We provide two types of guidelines. First class we call functional guidelines, which deal with overall problems like power distribution and grounding. The second set of guidelines refer to device or piece part problems. We've only touched the major problems here. We didn't try to make a comprehensive compilation of all the problems, but it does serve to spot some of the more common problems and hopefully help to remove those early in the design phase. Again, this can be done by the design engineer without really any prior experience in sneak circuit analysis. He needn't have any knowledge about coming up with network trees or applying clues to network trees. He would just merely review the guidebook. An example of a design rule. It is undesirable to have current interrupting elements in a ground path. It is a more desired approach like this. path is open, you are prone to having a sneak path, if you will, between multiple power sources. You're also open for having a shock hazard here. So a general rule given to the design engineer is to avoid, if possible, this type of configuration. An example of a functional guideline that the designer would review after initially working on his design would be the case of having a ground connection in an independent connector from the power connection. This was the type of problem that led to the Mercury Redstone launch failure, in which the ground umbilical disconnected moments before a power cable disconnected, causing the failure of the launch. The preferable solution is to have the ground connection and the power connections all in one physical connector. An example of a device guideline. One commonly, unfortunately, finds feedback from the output of a line driver back to circuitry on the board. This is a case where the signal is needed for other purposes on the board as well as going off the board. What may happen is you may get reflections on the unbalanced lines, which might cause an inadvertent triggering of the circuitry. The preferable approach is, if that signal is needed, is to provide it with its own path this way rather than taking it off the output here. What we attempted to do with our automated approach was, number one, to automate those functional and design guidelines, and secondly, to add the even more important and complex task of searching for sneak paths. Our automated system, which we call SCAT, currently implements about 17 of those functional and design guidelines. It's implemented as a knowledge base in an expert system. Being so, it's not very difficult to add more rules to it. So it's expandable. Our sneak path search program is implemented in a C program. It's very efficient. It can find sneak paths in a matter of minutes. We've implemented this on a microcomputer in a DOS environment. We chose DOS at the time because at the time when we did this, it was very prevalent, it was very available, you didn't have to wait for a workstation. Presumably a PC could be on every design engineer's desk. That was the advantage. Of course, the disadvantage of choosing DOS was that we could not effectively interface our application with other applications which would enable the graphical representation of our results. So consequently, the way our SCAT program is currently implemented, the results are displayed textually rather than graphically. The system requires a popular schematic capture product sold by ORCAD to capture a schematic and generate a net list in a format called EDIF, which is becoming a standard for generating net lists. The SCAT program reads in the net list and then generates two versions. One version for our expert system, which is used for processing the functional and device guidelines for design concerns. And a second version for our procedural code, which searches for sneak paths. The outputs of these are presented to the user using the windowing environment of the expert system shell. The procedure for using SCAT is summarized as follows. You must first partition the circuitry down to a size that SCAT can handle. SCAT is limited primarily by the memory in your PC. With a 1 megabyte RAM type system, we can handle circuits up to 300 devices as far as searching for design concerns is concerned, or up to 2,000 devices as far as searching for sneak paths are concerned. The second task is to capture that schematic using ORCAD and generate a net list of that schematic using the utility that is supplied with the ORCAD product. Also, during this schematic capture process, it's important to edit the schematic to provide certain information that SCAT needs in order to accomplish the sneak path analysis. And I'll get into that a little later. You then invoke SCAT. You specify the name of the netlist file. You enter in various modeling parameters. And then you run sneak paths and you run design concerns. These are two separate processes within SCAT. An example circuit. This is a circuit that was captured on the ORCAD system. Believe it or not, there's a sneak path here, even though it's not obvious. It involves this area here with the relay, and I'll expand upon that. I might also point out the portion of the schematic that was edited specifically for SCAT was the introduction of two nodes, one labeled SRC source, and the other labeled SNK sync. In order to find sneak paths, we must first trace all paths from a source point to a sync point. Typically, your source would be power, your sink and ground. If you have more than one type of power coming into your circuit, you would have to repeat the analysis, applying the source node to each one of those power inputs. You then have ORCAD generate a netlist. This is an example of an EDIF netlist. One portion of the netlist defines the symbols on the schematic, like for instance a transformer. Another portion of the netlist defines the connectivity. In this case, we say that node number 1 consists of capacitor C8 joined to resistor R7 joined to the base of transistor Q3. This ASCII representation of the schematic is generated automatically by a netlist utility supplied with ORCAD. Back to our problem. Under normal conditions, the goal was to control these two lamps as follows. When this transistor is off, and this switch is off, this relay is de-energized, and the current flow is such that lamp number 2 is on. When transistor Q1 is turned on, you now have a path to energize the relay, causing this contact to move down and now extinguish lamp 2 and to light lamp 1. When you now activate this switch, you can now take part of that coil energizing power and use it to relight lamp 2. now activate this switch. You can now take some of the power that was used for lighting this lamp and use it for energizing the relay, which would now cause the relay contact to move down, de-energize the lamp, but also de-energize the relay. And you'd sit there and oscillate. The reason why this sneak occurred is because when we design something, we frequently design it on how it should work, not how it shouldn't work. We don't test things for how they shouldn't work, we test them for how they should work. Sneak circuit analysis checks into those unexpected problems to make sure that when things don't work, that they don't cause undesirable events to happen. This is the main menu as it appears on your PC screen after you have invoked SCAT and specified the name of a netlist file. It's a windowing type system. The two major choices for the user is to specify whether or not he must perform a sneak circuit analysis or the design concern analysis. Other options involve specifying modeling of switches and modeling of capacitors. We will assume that we're going to select sneak paths. For that circuit, for the example circuit that I've shown, in a matter of seconds, SCAT produces the following results. It says that it has to find two branches that involve reverse current. We're looking at path number 1. It's defined in terms of the reference designations that appear on the schematic. If we now go back to the schematic and look at K1, S2, and K1 again, it's referring to this path, the undesired path. We now look at the next path, path number 2. It's specified as Q1, S2, LP2. We go back to the schematic. That is the desired path. This information is presented to the designer or analyst. It is now up to that person to evaluate this pair of paths to determine if that was the intent, and if not, if anything undesirable could happen. If, from the main menu, you select Design rather than Sneak, the menu that will then appear is the Design Concerns menu, where you have two major choices: functional guidelines, device guidelines, corresponding to the guidelines that I mentioned in the manual approach. The first thing that happens, the system finds a power-to-power tie. It specifies the path in terms of the reference designations appearing on the schematic. K1, S3, K1, S1, F1. If we now look at the schematic, where we've traced out the path, we see the path involves a tie between the AC power coming in and this DC power labeled source over here. The reason why that path existed is because we modeled this particular switch as a make before break type switch. The two basic types of switch contact arrangements are break before make, which is our default, or make before break, which the user can specify. In this case, since it was possible for two of the switch contacts to momentarily be shorted together in the process of switching, this momentary sneak path exists. SCAT finds it. If the analyst performing this analysis doesn't understand the ramifications of that, you can call up an explanation or a solution, which we have shown here. If you had selected device guidelines, you may get a display like this. This is warning the user transistors Q3 and Q2 have a problem of reverse current flow through a transistor junction that's normally reverse bias, but under the conditions that we had drawn on the schematic, could become forward bias. Again, you can get an explanation and a solution of the problem. In conclusion, we believe that with this tool, we can integrate sneak circuit analysis with the early phases of design. We feel that the analysis can be performed by people who are not necessarily proficient in sneak circuit analysis. Okay, we can get timely results that can be fed back into the design process and make the modifications to the circuitry to eliminate problems while it is still inexpensive to do so. We also have provided an interface with a standard computer-aided design tool. SCAT program can be used as a first cut to remove problems early in the design before a more intensive analysis is applied. We hope for the future to expand the program, to expand SCAT by including more design concern rules in the knowledge base, by porting it to an environment in which we can graphically show our results right on the schematic rather than textually, and to upgrade our EDIF interface to the most recent release so that we can be compatible with schematic capture programs other than ORCAD. Will give you the manual approach along with a floppy disk containing the SCAT program. You must provide the M1 expert system shell, however, to run it. And if you wish to do more than just evaluate the demo netlist, you would also need ORCAD to generate your own schematics and netlist.
certainly must be some limitation in your ability to provide that from whatever CAD software you're going to pull it from. Apparently, you're transferring these to the capability of operating on DOS, for one thing, and this may not be direct compatible. Are you just interpreting these on ASCII files, or just what do you do?
Well, when we started out, there were two basic approaches we could have chosen for developing SCAT. One was to integrate it intimately with the schematic capture tool. Then we would be, though, dedicated to using one tool. The other approach was we hoped to find some sort of universal format that many vendors could generate. At that time, it was EDIF version 110, which was an early version of EDIF and left a lot to the imagination of the person writing the program. Consequently, that EDIF 110 that's generated by ORCAD is really ORCAD specific. Since then, the EDIF committee has come out with version 200. 200 is generated by a large number of schematic capture products. We haven't upgraded our system yet to read in EDIF 200, but it's not very difficult to do so. When we would do so, then we could accept net lists from a much wider source of schematic capture products. Also, we would want to take EDIF, which is now on a PC, and write it for, let's say, a workstation environment, because today you find more and more work being done on a workstation. As a matter of fact, the workstation is now becoming more and more prevalent. And there is a vast number of products, of CAD products that run on the workstations. So we would want to do that. It wouldn't be a simple matter of just porting the system from DOS to a workstation. It would be some major design effort, but that's something we hope to do.
Yeah, but you represent the schematic. You said, hey, we have these two paths. How do you see these paths in your interpretation? Because you're not looking at the schematic per se.
Right. We present the user a textual representation of the results. The user then uses the sequence of symbols. He has to then trace on his schematic that path. Now, what we're counting on is that the user is not just let's say, a reliability analyst just called in at the last minute. What we are hoping is that the user is either the design engineer who designed that printed circuit board and is intimately familiar with the circuit, or a very experienced reliability analyst who has been brought up to speed on that circuit, who understands that circuit. SCAT really is not meant as a tool for the novice as far as the circuit is concerned. It is meant as a tool for the novice as far as sneak circuit analysis is concerned. You don't need to know what sneak circuit analysis is all about, but what you do have to understand is circuit design engineering.
Yeah, but I still don't understand how you interpret in your EDIF file this circuit.
Okay, how does our program come up with that result? What we do is as follows. We trace using a very efficient algorithm. We trace all paths from the point designated as source to the point designated as sink. Every topological path, taking into account nonlinearities in the topology, namely, say, diodes, transistors, other nonlinear devices that would permit only signal flow in one direction. We take that into account. We model all transistors, a large number of devices. We automatically model those in terms of their switch diode equivalents. So now we have, in mathematical terms, we have a graph, and we find all paths through this graph. The second thing we do is we take a look at all those paths and see which of those paths have common segments. Then we look at those common segments to see if our tracing, if our signal flow is in opposite directions through those common segments. If that is the case, we refer to those segments as either reverse current, as one of them being the reverse of the other, or as bidirectional. This is a bidirectional segment because under one set of circumstances, current is flowing, you might say, from left to right through that segment, while in the other case, it's flowing from right to left. Those bidirectional pairs are what are presented to the user. It is now up to that user, who we're counting on being being very familiar with the operation of the circuit. It's up to that user to now look at that and determine whether or not that's a problem.
All right, Jeff, I'll ask you three questions. The first is, how do you handle LSIs?
We have been enhancing SCAT following the conclusion of our contract with the Air Force. We've used SCAT on several sneak circuit analysis projects. We've been enhancing it, and one of the enhancements was to provide a simplified model for certain ICs. The reason why we didn't undertake it during the original contract was because there are so many ICs, we didn't have enough time to do it. As we find time, we're adding models to SCAT. One of the models that we've added is a model for an operational amplifier. So now, using our own version, now you won't find this in the RABC version, but in our own in-house version. Now, if an op-amp is present in your circuit, you can leave it in there, and we can automatically model it with its switch diode equivalent. With time, we'll be adding more and more models. This is something that we do. We have a modeling file, an ASCII file, which makes it very easy for us to add models. The modeling code is not, let's say, C code. It's just an ASCII file. We have set up our own format for adding models using our own, you might call it our own model programming language. And as we find time, we keep adding more and more models. But right now, the only IC that we've modeled is an op-amp. I might also point out that sneak circuit analysis originally was most successful in power distribution or power switching circuitry, which really didn't involve much in the way of integrated circuits. Today, people are trying to use it more for more in the way of integrated circuits, not just tracing power flow, but to trace signal flow. As I mentioned, SCAT currently can only automatically handle op-amps. If you want to make it handle other devices, you would go back to your original schematic in ORCAD, and you would have to remove those symbols and replace them manually with your own switch diode equivalents.
The other question is, do you have the capability to read in wireless? Because you won't be able to identify snake paths if you can't tie in the various cards.
One of the important points is that if you are looking, let's say, at a printed circuit board, in SCAT, because of the memory limitations, is usually limited for a snapshot of, let's say, the size of a printed circuit board. But what do you do about the interfaces? You have to model those. Now, it doesn't have to be limited, let's say, to a circuit board. You can limit it to, let's say, a function that may cross the boundaries. But that would have to be captured in a single ORCAD file. If it's not captured in a single file, you have to, or the design engineer, let's say, would have to supply a simplified model of those interfaces. For example, let's say an input to the circuit is a switched power signal. And let's say it's switched by some complex arrangement of transistors. You could simplify that by just saying I have power going through a switch. And that's what you would have to add to your schematic. You could either add it to the schematic or you could add it to the net list. but it's much easier if you add it graphically to the schematic and then generate the net list on that. So for all the interfaces of whatever your boundary is, let's say it happens to be a printed circuit board, you have to supply models for signals that are either coming into that board or for the terminations for signals leaving that board.
There's a request, and you probably know about this, to apply SCAT to an entire flight control system. Do you think that's realistic? Is that a realistic endeavor?
Yes, the problem was not to apply SCAT to the entire flight control system. That we could do. The problem was to apply SCAT to critical areas of the flight control system, where those critical areas have actually been mapped out. And if you just confine it to that, then the scope of the problem is much less. And if your problem is well defined like that, then you can do it. But if you have a large system and you don't know where critical areas are, you just say work on the entire system, then you're going to be possibly running into a problem. You can't capture the entire system in ORCAD. And it would be pretty difficult to model everything. Now, also keep in mind that the primary intent of SCAT was not to trace signal paths through data buses, address buses, digital circuitry, microprocessors. That was not the real intent. The real intent was to trace paths from power to critical loads. So if we just concentrate on that, SCAT can handle that problem. If we want to trace sneak paths, which is very rarely done, if at all, if we want to trace sneak paths through memory devices, microprocessors, that kind of thing, SCAT couldn't do it, but I have a hunch there aren't many tools that can trace sneak paths through that level, unless you have very good models of all these devices, or unless you make grossly simplifying assumptions about the technology. And you also keep in mind that sneak circuit analysis assumes that there are no failures. We are not addressing software. So because of that, we're assuming that all software, firmware, is working as designed, that there are no problems. So we would draw the boundary we would not include the microprocessor in our analysis, but we would start at the output, at the signals being generated. We would assume that all timing coming from the microprocessor is working, because we're not going to trace sneak paths through these complex devices.
Are you considering the subject of sneak paths software as a subject for your concern?
We haven't. We've concentrated primarily on the hardware. We feel that there are other tools available to the software analyst to use that would be as effective, if not more effective, than sneak software analysis, and are much less expensive to fault tree analysis, various the various processes that are involved in reviewing software. Before you would want to go through the task of modeling your software in terms of symbols that can be used in a sneak software analysis, which is a pretty big undertaking. We feel that perhaps a better approach would be the more conventional task. Look at it, let's say, from a top-down functional point of view. In any event, we have not pursued that.
Okay, thank you very much.
Thank you for we model,